Hey everybody, we're going to get started real soon. So thank you for coming out. This is one of machine learning at Berkeley's first Tech Talks, and it's great to have Aaron Hertzmann here. And yeah, that's pretty much it. Please take it away.
Well, thanks a lot for inviting me over here. It's a pleasure to speak to you. I'm going to talk about work in artistic stylization. I'm sure you've seen all the really cool stuff that's coming around in neural stylization, and I'm going to get to that later in the talk. But I think it's always can be interesting to hear where things came from, hear about the history, and also if you're trying to think about where you might want to go in the future, how I got to doing this stuff as well. Feel free to ask questions along the way if there's anything you're curious about. This is going to be a fairly high-level overview of a whole bunch of different research projects rather than drilling into one or two in particular. So the math is, if you don't follow it, it's okay, but also feel free to ask questions. And I also have a lot of references I'll be showing. I'd be happy to provide a list of references later if you want. So when I went to college, when I was an undergrad, I double majored in art and computer science. So I spent a lot of time programming and I spent a lot of time painting. So this is painting with physical media and real brushes. So this is just something I enjoyed doing, I found interesting. And people often said, when you graduate, you must be doing computer graphics because it's like art and computer science. And I was like, no, these things are totally unrelated to each other. The active programming and painting a picture seem like they have nothing in common with each other, have nothing to do with each other. Anyways, that's how I felt at the time. And I started looking for jobs after graduation in computer programming, basically, and all those jobs seemed really boring, so I went to grad school. And I did like computer graphics, so I decided to do that. And I was interested in computer vision at first, looking for a project in that. But then I attended SIGGRAPH, which is the main conference in computer graphics, and I saw a talk where someone was describing a method that would start with a photograph and generate a painting from it by placing a bunch of these little brush strokes around the image aligned with the image gradients and copying the colors. And I was sitting in the talk thinking, well, that's not how artists work at all. So I went back to school and started just playing around and coding stuff up. And I came up with an algorithm that implements, in some sense, my intuitions about how I place brush strokes when I'm painting. So it would start with a photograph, and the algorithm would place a bunch of really big, fat strokes to match, from the image, the way that previous algorithm had. But then it would look at this and see where it had made mistakes, and it would place lots of smaller strokes, especially around edges or contours of the image, and keep refining it, and so we get this refined final result. And then we can also replace that algorithm when it draws long curved strokes. So this is basically an algorithm designed which is coded up a whole bunch of heuristics or rules based on my intuitions for how painters work. And one algorithm that you can implement yourself if you felt like it for some reason. And this is my first technical publication. And I implemented actually a version of this that you can walk up to, and it's a live painting that refreshes a painting every moment, and so more and more brush strokes are drawn as you move around in front of it. And actually, this was 16 years ago, but recently I found an app in the iPhone App Store that, from what I can tell from what they wrote, is basically an implementation of that old algorithm, but now runs on the phone. So this is an instance of what in the computer graphics field we call non-photorealistic rendering. So how do we develop computer rendering algorithms that mimic the way that artists work to produce paintings and drawings, cartoons, and illustrations. And the belief is that as compared to conventional photorealistic computer graphics, natural illustration styles can have a lot of expressive power, a lot of beauty, and a lot of artistic merit in ways that ordinary photographs do not. So as a research area, we have three real goals here. We want to understand the science of how people create art. Why is it that an artist chooses brushstrokes in particular ways? And the linear perspective model, like if you've taken computer graphics or computer vision, you've learned about. This is like the very simple Renaissance era model for drawing, but there's a lot more to understand about how artists choose brushstrokes the way they do. If we can do that, then we can build better algorithms that will automate the painting and drawing. And that will allow us to create new artistic tools, create new kinds of video games and movies and TV shows and VR experiences that draw from the expressive power of traditional media, but creating new experiences that couldn't have existed before. And sometimes it scares, occasionally it scares people for some reason. They think that we don't want AI taking our artists' jobs. But I think the better way to look at it is that as we develop new technologies throughout the ages, we've always developed new and exciting art. People at first might have thought photography would put portrait painters out of business. Well, it did, but it also created new kinds of photographic art forms. And the same for style animation and computer animation. Okay, so in this area, one of the most basic things you can do is render a 3D model, because now we have access, in terms of understanding art, we can reason about what would an artist do if they knew the 3D scene that they're drawing. And the simplest obviously called included contours. Including contours look like this for that 3D object. And if you had occluded contours, you can also stylize them and draw them in a more artistic way, or stylized way. The occluding contours algorithm is arguably the oldest computer graphics algorithm. It goes back at least to 1966. So these are from a paper back then that rendered this very simple mouth shape. And there's a simple differential geometric formulation of how you draw them. It's a very, very simple formula. And if you're not familiar with the differential geometry, then it's not important for the rest of the talk. And the basic idea is if you have a 3D surface that you're viewing from a particular viewpoint, then we want to find the points that are grazing angles to the viewer, or that is, for which the surface normal is perpendicular to the view direction. And this red curve here would then be called the occluding contour. And so,
I just had a question about the
sure.
image 3 slides ago or so, the one with the stylized contour. Is there a reason you would do the stylized contour, or is that just for just for different artistic purposes?
For different artistic styles.
Okay.
Yeah. And there'll be lots of examples later on.
I see.
So here's another example of that visualization. In the upper left, there's a view of a torus as with essentially a headlight. So the frontoparallel regions are bright and the edge-on parts are dark. And the edge-on parts are the regions where the contours are. So if we extract those curves and render them, we can get a rendering like that. And then we can go beyond that. So there's a method called suggestive contours that has also some really elegant math behind it. Without getting into the details, it looks like that. And so there's a very essentially simple formulation that in the end produces a set of curves that looks a lot like a line drawing. In fact, there was a study done in which researchers asked a bunch of art students to draw line drawings of 3D models, and they compare those line drawings to the ones produced by these algorithms, and these algorithms predict about 80% of the curves that they drew. So which is, I think, really, really good. We're actually, with very simple principles, we can get very far into describing the curves that artists draw. Having extracted those curves in 3D, there's all these curves in the surface. It's very hard to understand this picture if you haven't looked at it for a while. A lot of those curves are invisible, but if we hide the invisible curves, we can see the 3D structure of those contours. And then those we can stylize and then animate. But the algorithms involved in doing this are fairly involved. The formulation is very simple and elegant, but the algorithms are quite complex, unfortunately. But then the nice part about that is we can define all these artistic styles on top of that formalism, that the different choices for how we draw the strokes and fill or shade the interiors of objects give us different artistic styles. And of course, they can be animated. So this is all with the same algorithm. Different strokes were selected, or different procedures for drawing strokes, and you get this really lovely set of styles. One place where this has been used in the way of the real world is this Paperman short from Disney that won the Academy Award a few years ago. And here, artists drew each of the curves, holoslice and picket frame. So a little fiddly. So each of these curves here was drawn by an artist on a 3D model, but their motion through time is tracked by one of these algorithms. So all these methods I describe are essentially procedural. One writes a bunch of code to describe the model you have in your head about how you think artists will draw curves. And as you can see, there's a lot of really nice results you can get out of it. And you can get a lot of very precise control over having the strokes appear in the places where you want. But on the other hand, it's hard to design these styles and say like, okay, now I want to make a Van Gogh kind of animation, or I want to make it look like a Picasso. What are all of the formulas that describe all the choices that those artists make? That seems really hard. I don't really know how to come up with algorithms for all of that. And also, as I mentioned, sometimes these algorithms can be fairly hairy to implement. I mean, that's kind of a subjective consideration. When somebody has a nice implementation on GitHub, and it's easy to implement, but that doesn't exist right now, and it's hard to implement. Okay, so how can we get move on in terms of better or richer space of artistic styles? So in order to address that question, we're actually going to take a total detour to something completely different, which is the question of how do we make textures? And back when I first started learning about texture modeling, texture analysis, I was in grad school, and I went to research seminars about texture, not thinking that it would have any relevance to my work, but just because I thought it was really interesting. Sometimes you make these connections where you just learn about stuff because it's interesting, not knowing how to use it, and years later you might discover connections or realize connections that you wouldn't have anticipated in the future. And that's the case here. So the question in understanding texture is, so we look at a texture like this, we could all probably agree this is a texture. I think we could all recognize some kind of wood grain, probably a table of some kind, or side of one of these posts maybe. And so many ask the question, well, how could you tell it's a texture? You haven't seen probably this exact texture before. The placement of the grains is probably not important, but somehow something about the statistics of them seems relevant. And same for most of the other things you might describe as textures. A lot of them have patterns of rocks or bricks or weave or pebbles or something that the individual details of these things are not important, but the fact that there's a whole bunch of them somehow describes that. So how do we mathematically formalize that intuition? Okay? And feel free, if there are any questions, feel free to jump in. So this is something people in vision have thought about for decades. The earliest models, and the simplest thing you might do is think, well, if this is a statistical phenomenon, then let's tabulate what pixels happen to occur next to each other once and build tables. So people would build histograms of which gray levels in a grayscale texture occur next to each other once. Look, this dark pixel tends to appear very often next to a dark pixel, or really next to a dark pixel that would sort of represent the amount of smoothness in the texture. Obviously that model is a little bit primitive, but then things started to get actually pretty effective when people looked at histograms of filter responses. So it may not be very clear from this image, but if you take like this little patch here and filter with a bunch of these different convolutional filters, these are essentially edge detection filters at different orientations and scales, you get all these different filter responses, and they identify which parts of the image have edges in different orientations and edges in different sizes. And so this method by Portier and Simicelli from 2000 built a whole bunch of aggregate statistics of where edges occur in images and how they co-occur with other images at other edges at different scales and at different locations. And they're always quite hairy and complicated, so I will not go over it. And I'm also not learning in preparation for this talk because I don't want to. But they started to get some nice results. So starting with this texture, if they build these histograms of statistics of image filters and then extend the image by optimization to kind of preserve this kind of filters, we get a new texture out from the original one that recognizably looks like the original stuff. On the other hand, though, it's still not quite there. You're not going to want to actually buy those peppers. But it's really, it starts to look like something's going on. So, as I mentioned, these methods are getting hairier and hairier. It's expensive, it's hard to think about, hard to reason about what is it doing or why it works. And it's hard to figure out how to improve past that, it turns out, if you think about it for a while. And so, the next advance in this area came from actually Professor Efros when he was a student at Berkeley. And he had a very clever idea. It was completely different from the other thing. And like a lot of these methods, it's the sort of thing that if you had described it to me before I saw the paper or the results, I would have said, well, that's crazy, that'll never work. And then you see the result and it's amazing. So in this case, the intuition is, suppose I want to describe what that output texture is in relation to the input texture. What we'll do is say, suppose you look at any window of pixels in the output texture. In this, it would be in the original order, like 19 by 19 patches. I want to produce the output texture such that every patch looks like some patch in the input image. Doesn't matter where it is, and the two pixels next to each other in the output image might look like different patches in the input image. But as long as any window as long as whenever I look at the output texture through some window, it looks like the corresponding window in the input image, then I'm going to get the nice results. And the algorithm they proposed, there's a couple of different variants in it. And this is just one simple way of explaining it. You generate the output pixels one by one, and in scanline order. And to produce the next pixel, you take an L-shaped window around that window in the output, and then look through the input texture and find the window that looks most similar to the L-shaped window in the output, and then just copy it center pixel over. So this is kind of the simplest version of the algorithm. There's a lot more sophisticated things that I'm not going to talk about right now. But that's the basic idea. Does that idea make sense?
How do you search through the input texture to find a segment that looks like what the window is actually looking at?
So the simplest thing is to just try every single window. That's very slow. It's slightly better to use nearest neighbor data structures that accelerate that search. So in graphics and computational geometry, there are algorithms that will let you take a vector of values, put it in a data structure, and find, after generating the data structure from all the different neighborhoods, find the one very efficiently, which is closest.
Okay.
And then I'm going to mention quickly later, there's another algorithm that makes it much faster than that.
So you can vary the size of that filter, right? Like you can just
Yes.
make it abstract size.
Yeah. And actually, so the more efficient thing, so this is the white paper, where they generate things in a coarse-defined way. So they start with a low resolution image, and then generate a higher resolution from that with a window which is square in the low resolution version, and L-shaped in the high resolution, and they iterate.
Oh,
And then they can use 3x3 or 5x5.
and that would give better, more genuine results of patch generation then?
Yes.
Yeah.
So these are the results from Way and Lavoie's method, inputs and outputs. And you can see that it's starting to look like, again, kind of magical, I think, from such a brain-dead algorithm. On the other hand, there's also ways in which they're not perfect. It's not really getting these cracks at all. It's not getting the structure in the cracker in the upper left, although maybe that's a plausible result anyways. So when I started seeing this, I actually thought about using this algorithm for curve stylization. So what I was thinking at the time was, I want to draw the squiggly strokes that artists would draw, and I want to use the same kind of texture procedure to synthesize strokes in 1D instead of 2D. And I started to think about, this is my old slide from way back then, where I was thinking about rotoscoping and having an artist draw over a curve in one frame of a video, and it would automatically generate the corresponding curve for another frame in the video. And then so I thought, well, actually I should condition the output curve on the curve, because if the person's face changes the shape, then this curve should change too. And then I started to realize the algorithm I was thinking of actually would apply for images. It'd be a lot more interesting. And so, long story short, the algorithm that I came up with was something we called image analogies. And the procedure the problem statement can be described as follows. You give me 3 images, the A, A prime, and B. I want to produce B prime such that A is to A prime or B is to B prime. Another way to say this is I want to learn an image filter. So I think of the A prime image as a filtered version of A. I want to learn the filter that produces that and then apply that filter to B. And then see what happens. And the algorithm that I came up with is a very simple extension of the ones that I just described. So I want to have that same property before, that every patch in B prime looks like some patch in A prime. But I also want to have that be condition on the patches in B. And this may take a little while to wrap your head around. But essentially I want both those two patches together to look like some pair of patches in the exemplar pair. So in other words, if there's an edge, a vertical edge of this patch in B, then I want to copy texture from a corresponding part of A that also has a vertical edge in it. The algorithm based on that is quite similar. We iterate over the pixels to produce B prime in a raster order. But now we look at both the L-shaped neighborhood of pixels around the output pixel array, together with a corresponding square patch around that in B. And we search again through A and A prime to find the corresponding patch that best matches that output patch, and then copy that pixel over. And this could also be extended with the same multi-scale procedure that is briefly summarized just now. So although I've been focusing on stylization, this is really in principle a procedure for learning any kind of image filter. So a simple sanity check is we feed it a blurry version of the input image, and it produces, it learns to essentially blur images. We can also learn to add detail to a blurry image, go the other way essentially, go from blurry to sharp. More interestingly, we can use it to essentially generate texture that looks like an image. So this is essentially, you can think of it as like texture synthesis, but guiding it to sort of follow the tone in that the image B there. Okay, so artistic stylization then is the thing that I was focusing on though. So here I was lucky enough to find a whole book that has a photograph and a pastel drawing of that photograph with it, or pairs of photographs and pastel drawings. And I wanted to stylize this photograph. Now here the problem is that the color space in the Swan pastel is nothing like the pastels in the target image. So if I try to match patches between these two, they're not going to align up at all, because there's no green stuff in the, none of the sort of yellow-green stuff shows up in the Swan. So in order to address that, we can make use of an observation from perception, which is that if you take an image and split it up into luminance channels and color channels, then we're much more sensitive to changes in the luminance image than we are to the color image. And here I just use Photoshop in the LED color space to split these up. So we can illustrate that by taking this pair of images and blurring the color channels and reconstructing the image. And you probably, from a distance, you can't even tell if there's much of a difference there. And maybe I can zoom in. You can see that the area around the tree that has a bit of a green halo of it that wasn't there before, but it looks pretty much the same. Whereas if we were to instead blur the luminance and keep the color channels the same, then the image looks really blurry, even though this is perfectly sharp. So the resulting procedure then is we start with our input photograph and just the luminances from the pastel image. Extract the luminances from the target photograph. Run the analogies synthesis, texture synthesis procedure on those to produce this pastel texture grayscale image. Also get the colors out of the original input image, combine them, and then we get this result. So here we have something that I would argue both looks like the scene that's being the photograph in that scene, but also has that painterly or that sort of stylized abstraction, like you can recognize individual pastel stroke texture in here. One funny thing that happened is that here in our exemplar pair, we have a case where pure white on the swan's back gets mapped into feathered texture. In the sky, we have a pure white region, and we get feathers in the sky. So the algorithm doesn't really know anything about object identities, and that's something that maybe could be fixed up in future work. Any questions about that?
Yeah, can you explain again what was the purpose of blurring the color channels?
I'm just doing that. I was just doing that in order to illustrate the fact that we're much more sensitive to changes in luminance rather than color.
Right.
It's not. The algorithm itself doesn't blur anything.
Okay.
Here's another example. Here we didn't have an input photograph for the painting in the upper right, and so we just blurred it and called that the input. And so this produces a result here. So that's this image. We can also adjust weights in the algorithm to produce an image which looks less stylized, more photorealistic, or the opposite. actually, this was a troublesome image because we really liked this result, and we contacted the artist to see if we could use the image in the paper, and he said no, and we like begged him, and he's like refused to let us use the image, and so we like, after the paper was ready to be published, we're like scrambling, or actually I'm scrambling to try and find other images that this method worked on. Fortunately, it did work on other images, but we were thinking about, you know, saying something nasty about it on the paper, but we didn't. Here's an example of a line drawing. Also, we don't have a source image, so we blur the input. And in this case, we can generate here a line drawing of the butterfly. And the nice thing is, one algorithm works for all these cases. Whether or not you want to call it learning or just nearest neighbor patch copying, either way, it's working with data. And one fun thing about when you start working on a problem or any kind of project, and you really intensely, you often kind of like tend to see that thing everywhere you go. And so I was like taking a break one weekend and went to a friend's office, and I saw this poster hanging on the wall, and immediately I thought, oh, textures. And I thought, well, we can use the exact same algorithm with this. I'll draw the guiding image being sort of masked into the white and dark regions, and tell it now produce this, now work from this map. Essentially what it's saying is generate path texture in the white areas and brush texture in the background. And it produces that.
That's sick.
Now, the problem with that, of course, it hasn't really noticed that there's this depth effect here. The bushes here are bigger than the ones in the back. So we add a depth channel to it as well, and then it will also generate things that receive distance.
Where did it get the color from? Because previously you were saying that you just used the color from your input image, but that was a black and white input image, and then you got green color out.
In this case, I'm using the raw colors in each pair of images. So this I just drew by hand in Photoshop. And this I'm just matching the RGB colors.
Okay, so you don't do luminance.
What do you mean by depth channel?
The red channel there. It's not actually depth, it's just like a linear gradient.
Oh, okay.
It's
Yeah,
just
I thought it was a reflection from the bottom.
Yeah, I thought you didn't see that.
Yeah, I guess we can't really, we don't know how to chop these lines, so. Yeah, that's fine. So we can make the control channels more and more complicated and rearrange Washington or do whatever else. We also came up with a interactive version. So this is 16 years ago, so we had to do a lot of weird hacking to make it run real time. Now it'll be much faster, but here you specify the arrangement of things you want, and as you do it, synthesize these textures that correspond to what you're drawing. So I complete the arch. Okay. One other key development that I just want to briefly mention that came a bunch of years later from my colleagues at Adobe was something called patch match, and it actually speeds up the algorithm with mentioned the nearest neighbor thing. Really, it makes it really fast. And they have all these like lightning fast live demos even 6 years ago, and this became the feature in Photoshop called content overfill that was really popular at the time. So if you want to understand how to implement those things fast, it's worth checking this out.
Super cool. That was really cool.
They have a lot of other super fun demos in here, like rearranging buildings, fixing the top of Parthenon. That's all fixed. Okay, well you can check that out on the web if you want to see more. Okay, well let's just viewer windows. So here they're obviously specifying line constraints on the result, so we get straight edges. Anyways, you can watch that stuff all day, but many other things to show you. This is an example that was done by some of my colleagues at Pixar who were also working on applying the same analogies technique for character animation. So here they started with a 3D animation, and for this they know the exact geometry of the scene, they know all the motions of all the points of the scene. They had an artist digitally paint these keyframes for a subset of the frames of the animation, and then they run a synthesis procedure like what I described, but it's designed to preserve the texture of objects as they move during that synthesis process. So this is what it produces as a result. I think it looks pretty nice.
Yeah. So how do you feel about all these like neural artistic style transfer algorithms after years of like spending lots of hours working on the algorithmic versions of? It seems like the neural versions are just like taking all these traditional ideas in the field that they've been worked on for years and just throwing a deep net at them. How do you feel about that?
Excellent question.
Segue.
I know it's going to go on here.
Well, it looks like our time's up. Okay, so as mentioned, there's all these amazing things. Like since all that work I showed you happened, this huge revolution has been happening in neural networks. That suddenly it turns out neural networks are hot again, and they actually work. So, at a simplest level, how many people are familiar with like the basics of how convolutional neural network works? It's like maybe half or so. So the simplest way of thinking about it, or like just a brief overview, is you start with some image as it comes in. It goes through a set of convolutions, and there's some nonlinearities between each convolution. And so each of those convolutions is a set of filters. There's some other stuff that happens afterwards, which is going to turn out to be important. And the filters in those convolutions are learned on a large object recognition data set. So if we look at what those filters are, as the first layer are the same kind of edge and scale selective filters that I showed you before with the earlier texture synthesis, statistical texture synthesis methods. And they tend to respond to different kinds of edges and patches in the image. But as you go higher, like those higher level convolutions go up in the hierarchy, we discover these filters are essentially responsive to more larger scale structures in images. And even higher up we have things like, you kind of see a keyboard filter over there, and there's sort of like curve art and other structures that are turns out quite recognizable. So the question you could ask then is, can we go back to that whole statistical model of texture that we brushed off earlier and revisit that, but now with the filters that neural networks have? And so this is the idea that Leon Gattis and his collaborators proposed a year ago. I mean, it seems like 10 years ago, and yet, in research time, it's really very recent. So they would take a texture image and apply what is pre-trained neural networks to it to get filter responses at these different scales. And at each scale, you can get these feature responses or filter responses as a vector F, and then look at the correlations between them. So I stole the slide from Leon, so I'm not crazy about the notation. But you can essentially think of these as covariances of the feature responses across the image. So which filters tend to co-occur? So the same idea that was used before in earlier texture models, but now using convolutional neural networks. And they also found they're only using covariances. Previous people had used higher order statistics that are harder to work with. So in other words, which edges tend to co-occur, which keyboard patch, which other object patches tend to occur together. And then they came up with an algorithm which, despite the complicated diagram, is actually quite conceptually simple. If you want to generate a new texture, you start with some RAM noise, and then you keep improving that image such that its statistics of these covariances look similar to the input covariances. So that edges that tend to occur together in the input also tend to occur together in the output. And running that procedure produces these results that, they look way better than the texture methods that we'd all been working on before. So this is a little backwards. These are the input textures on the right, and these are the output textures on the left. So it's really impressive. And then they ran it on these methods these images which have a lot more structure in them. Like those curved lines, it's kind of amazing that it produces an image in the upper left. And it starts to look like there's more going on here than just, low-level texture. There's something more about the structures that are being preserved in the image. So that led these guys to think about stylization. And so they essentially use the same texture representation. Start with, in this example, a Van Gogh painting, and extract all these filters and their covariances across the different network scales. So to build a statistical model of the texture. And then the image that they would want to stylize, they also extract those filter responses, although they don't compute. Here they don't summarize in statistics, they keep the filter responses over the whole images. Now you can ask what information is present in these filter responses. And what they showed is, if you only keep around the high-level filter responses and reconstruct the image, then you get something like that on the upper right. So the filter responses are essentially keeping around the high-level structure of the image and throwing away like the fine-level details. So what they do is solve for an image that has the high-level details of the photograph and the textural statistics of the painting, and produces the painting there. And like, these results are, I think, totally mind-blowing. Again, if you just describe it, I don't know, like I have no idea if that method would have worked. And it's like way better than what you could have done with the patch-based methods that we had before. And like it really seems to just draw these new strokes that look like the strokes in the original, but none of them were actually, many of them were not actually present. In some cases, it does seem to be copying large patches like this album in the sky, but other things like the fine details are really, specific to the photograph being stylized. So I love this stuff. In answer to your question. So this method is really slow. It can take 10 minutes to generate a large image. There's been more recent things in the past few months that are learning networks that generate the output image, starting with a photograph. It learns a transformation model that generates the output image. The optimization, the objective in the procedure is to produce a network that preserves those statistics I mentioned before, but because the output is a network, it can be run really fast. The results are not as good, I think, as the slow optimization. So with Leon's algorithm, he preserves the structures of this input image a little better, whereas the feed-forward method kind of copies, repeats a lot of structure, like the sun randomly appears for no good reason. So the results are not as good with these feed-forward methods, but they're so fast, now there's like everyone and their brother has just released an app on the iPhone iOS store, like Prisma is the most popular one. There's all this implementation there. And just this morning, Facebook basically said that they're going to be doing this in a few weeks. So this stuff is huge and it's really amazing. But I think the results are not, there's a lot, if you look close at the results, they're not great. So, okay, so where does that leave us? We have these procedural methods I started out with, where we basically write a whole bunch of code and we get a few styles, but we can't really like produce, Van Gogh Starry Night. We have the patch-based methods that are a lot more controllable. You can specify which things you want to happen in which places, but a lot of situations the quality is not as good. And there's the new neural stuff, which so far, at least what we talked about so far, like the results are awesome, but you have no control over what you get. So the next question is, how do we get elements of each of these? How do we combine these benefits? So now I just want to talk about a couple of recent methods that have come out in the past 6 months or something, including some I've worked on. The first one is this thing called Stylit, which is for stylizing 3D models. This is from my colleagues at Adobe and elsewhere. And in this example here, to try to stylize that style image with that target image, then with the neural method, it actually doesn't do very well. And here the colors are in totally different color spaces, but even if things kind of work in the same color space. With black and white images, the neural method tends to blur things out a lot. It doesn't work really well for line drawing in a lot of situations. So what my colleagues came up with is essentially a patch-based analogies kind of method that uses all of the channels in a 3D rendering. So it only works if you're starting with a 3D rendering. You can't run it on a photograph. But when you do that, you can split up the source photograph into things like you can separate the highlight out, separate out the direct illumination, indirect illumination, and other effects. So that when you run the processing, and you do the same thing for the target, and then when you do the processing, the algorithm knows which strokes, which stylization was meant to be applied to the highlights, and which stylization is meant for shadows. And so it can produce much more faithful results. They also have a bunch of clever improvements to the details of the analogies algorithm. So if you actually wanted to implement analogies, I wouldn't use the algorithm I had mentioned earlier. I would use their method. So they can do hatching, they can do pastel, they can do something with some line drawing, although it loses the contours around here. And since we're at Berkeley, it can do this, the watercolor. And they can also animate it. It looks pretty good animated, although there's no attempt to make it temporally coherent. It just flickers, which is fine. So that's the direction of improving analogies. We can also improve the neural methods, or we can combine them. So there's one approach is to take the analogy algorithm, but run it on the neural network filters, and that's one way to get the control to specify the arrangements of textures. Another thing we wanted to do is to do something a little bit better with color than what the neural method work does. So we did this in collaboration with Elliot Checkman himself and Leon and his advisor. So if we start with these two images, so this flower garden, we stylize it like the Van Gogh. With his previous method, we get this blue flower garden, which probably, like if you had taken Van Gogh to this flower garden, he probably would not have painted it blue. I mean, who knows what would have happened, but I would guess that he would have chosen colors kind of like green, kind of like purple for the flowers. So we basically did the same thing that I described earlier for analogies, that we separate the input image into color luminance channels, do the stylization in the luminance domain, and then recombine with the color channels, and then we get this image out. So we preserve the painterly texture of the brush strokes from the Van Gogh painting and the colors from the photograph. Now obviously this is unsatisfying in some ways in that if Van Gogh painted that scene, he may have done something more wacky with the colors than just copy them. And it doesn't preserve the coherence of individual strokes and their colors. So there's more to be done, but I still think it's a big improvement over what happened before. We're also working on providing more of the spatial control into stylization. This is just very preliminary work, where if you stylize the photograph at the top with the painting at the bottom, what the current neural style method does, it puts a lot of the ground texture into the sky and looks kind of weird. It doesn't really make sense, even though there's perfectly good sky up in that original photograph. So if we're willing to specify a mask to separate the sky from the background, from the foreground, then we can modify the synthesis algorithm to respect that when optimizing different regions. And here it copies sky in the sky and house into house, and I think it looks a lot less weird. Yes.
So Aaron, the neural network should know that the sky is the sky, right? And it's probably in ImageNet trained one at least knows how sky, lawn, So why is it that you need to specify it by hand? Why couldn't it just figure out, I need to match sky to sky, building to building?
Well, I mean, that's an excellent question. So the short answer is I don't know, but I have a bunch of possible answers. One is it might know which is sky, which is not sky, or it might be, that signal might be in the filters, but it knows a lot of other things about these patches, and it doesn't really know that that's the most important thing that we're kind of telling it here. Maybe it doesn't know it's sky. I mean, it could probably figure it out. Yeah, and
so you tried doing it with just looking at the semantics and it didn't work well.
Yes. Well, I mean, that's what was sort of manually specified here. We experimented a little bit with explicitly applying semantic labeling, and that hasn't worked so well as you might have hoped. We can also copy from another sky entirely, and then have a different sky for this image. So it gets a little bit of control of mixing and matching different styles for different parts of the image. There's actually another paper which looks really cool that was just posted online 2 days ago and on the Google blog this morning, where they're learning a single feed-forward network that has a bunch of input parameters that will generate different styles as you adjust those parameters. So this is a different kind of control that will let you interpolate between these different styles. I mean, none of the individual images I think look very good. They don't really look that much like a real painting to me, but it seems like it's a step in the direction of really being able to provide finer scale control than just copying a single style. Yes?
How long would that take to generate?
Do you mean, so this is a live video from that paper?
Oh, that's live?
Yeah.
Oh,
Sorry?
I said wow.
Okay. Agreed. Another question, how do you apply it to animation? So there's another paper that just recently showed up where they tried stylizing each frame of a video completely independently and it looked really flickery. If they add some of the same temporal coherence stuff that we used to do back in the procedural NPR, then they can make more coherent animation. And I feel that at first this stuff looks really cool, but the longer you watch it, the weirder it looks. Because you kind of get this sense of, because it's so faithfully trying to move texture around to match the way that the real scene moved. It doesn't feel like a painting or a drawing that's been made of a real scene. It looks like a scene that's like covered in paint. This looks weird for other reasons. This is another example that someone else, using the GitHub repo applied to live video. And this, I think, really becomes clear that it just feels like these actors are covered in pastel or chalk, like they just came out of the mind. It doesn't feel like an animation of a real person. So this is something that we still have to figure out what to do.
Can you explain a little bit more how the temporal consistency is itchy?
Sure. So the basic intuition is, from a video sequence, you can compute what are called optical flow vectors. So for any point on an object, you have a vector for correspondence between frame 1, it appears here, and frame 2, it shows up there. So in the optimization that produces the stylization for each frame, one of the constraints is that the pixels in one frame should match the corresponding pixels in the previous frame, so that, like, if you're just moving horizontally, then all those pixels will just move without changing. Does that make sense enough?
Yeah.
Let's see. I think, okay, so this is time to mention a few other things. One sort of complementary area I've worked on a little bit is style recognition. So in computer vision, there's been tremendous progress in recognizing 3D scene descriptors. This is a car, this is a bus, and this is the road. Or for this, for some reason, this is the example image from the VOC challenge. Like a very important scene to do recognition, apparently. You can recognize the person in a bottle and so on. But obviously, I think that, as you may have guessed, I think that the style of an image is also really important to the information it conveys. That an image can be romantic or scary or haunting or funny or cute. And so we developed a data set a small data set to do style recognition. And this is, we were working this still when I thought, neural networks were still kind of like, not sure let those things work or not. So we gathered images that are sort of horror images, romantic images, and HDR style images. And this work was done by Sergey Karyev, who was a PhD student at Berkeley at the time. So we built these classifiers, and we tried things like, at the time we would have thought that color is like a really important classifier, and color features and other sort of low-level features. And it turned out neural networks trained on ImageNet for object recognition worked best. So here are examples where we could retrieve from our test set images that are minimal or melancholy or vintage. So there's essentially correctly classified as such. Or we can combine that same classification with other things. So we search for a dress, which looks vintage or noir, or search for flowers, which looks serene or geometric. And the same procedure also works for classifying paintings as well. One thing we're working on now is working with this data set from Behance. Behance is a website that professional artists and designers use to share portfolios of the work. It has millions and millions of images in it with textual descriptions. So we're working on building a data set that we can train style classifiers from. This is not relevant here. We're not working with Pinterest. Yes?
So earlier you said with the Van Gogh flowers, right? You may have painted with different colors. Have you tried adding to the constraint on the optimization of the image that you're producing, that you would also like to maximize the ability of the, let's say a third network to recognize Van Gogh's paintings, you'd like to maximize its confidence dually while also transferring the style?
We haven't tried that, and that's a great idea. There's a method for feed-forward network synthesis based on generative adversarial networks, which is kind of like what you described. But, I mean, you should just try it and find out. This is still the Wild West. I mean, there's so many good ideas here that haven't been tried. There's a whole bunch of, so I've been focusing on stylization, artistic stylization, but a lot of them I think just briefly mentioned. They can also apply to photographic stylization by example. So Some of my colleagues at Adobe have developed a method for portrait style transfer. For example, you give it a photograph and a different photograph of some other portrait, and it can learn to transfer this style in that image, or Zuckerberg style apply, or and they've also got methods for changing the time of day of an image. So here, starting with this photograph and time lapse of a bunch of other cities at night, they can produce what this city would look like at night. And one other brief example, you should look up later if you're interested in, is for using descriptive attributes like a style recognition with dimension to make outdoor scenes look more wintry or more autumnal or warmer and so on. Also, there's this whole other generative image method, which is like, I haven't mentioned at all, but also seems highly relevant and exciting. So this is also work from Alyosha, his student, and my colleagues at Adobe. And so you can just draw the outlines of the image you want in the synthesis model, and select the colors you want, and at runtime it produces images. And so the models here are very primitive in that they don't make super high resolution realistic images, but clearly like this is the way of the future. Like, this is really exciting stuff. And if you want to learn more about that, you can talk to Alyosha. So we're getting close to 8 o'clock. I want to wrap up. So again, as I broadly described, there are sort of kind of these three approaches to stylization. The completely procedural one, where you write a whole bunch of code and describe in code everything you want, or have artists draw outlines and move them around. The patch-based approach, which in some cases, actually, like with the style app thing I mentioned, right now is producing the best results, but it doesn't seem to generalize nearly as well as the neural stuff. The neural stuff looks great, but people are still right now figuring out how to really give it all the control that we want. And it's still an open question, like how do we do the best of all these methods, get all the control and all the range of styles, run really fast, and create amazing new forms of art. So broadly, like, if you're looking for problems to work on, there's just no end of things to try. We want to think about how do we author images. That's sort of the core problem. Either for novices to create new styles that match their phone, that go well with a scene that they just want to take a picture with on the phone, or for professional artists to create nice paintings and animate them. We want to learn style from large data sets, have fine scale control over style, improve the quality of the neural methods. There's a lot of cases where they don't really look that great. Make them faster, and then answer the scientific questions they started out with. What is artistic style, and what is texture? So I hope you find these problems as interesting as I do. There's more information about me if you're curious. You can just Google my name. We have a research website for where I work at Adobe Research, if you're interested. If you have questions about any of you want to know more about the things that I mentioned along the way in the papers, I'd be happy to provide citations and web links afterward. But I'd be happy to take any questions. And thanks a lot for sticking around.